Hi, it's Lasky from Malfeint Labs, and today we will analyze malware dubbed WhisperGate. It's a two-stage destructive malware discovered a few weeks ago, hitting some companies in Ukraine. It was first reported by Microsoft, and later samples were shared on VirusTotal. Today we will look at the first stage of the infection. We will see what it does and see if we can recover from it. I will link all the relevant samples and articles in the description below. I hope you will enjoy this video. Alright, so we will start our investigation, but looking at the sample from this Microsoft report from January 15, 2022. So this report actually tells you what the samples are doing, etc. So I will link it in the description below. You can read it, but I'm not gonna spoil it for now. So I will just dive into the bottom, and I will also link you this sample. It can be downloaded from VirusTotal, and if you don't have an account on VirusTotal, you can use a page called Malware Baazar, and this sample should also be here. I will give you both links, so you can find the WhisperGate first stage on Malware Baazar as well. I will give you both links, and I have this sample on my analysis machine already. So that's the stage 1 sample. We can analyze, you can make the initial triage by using PE Studio. And we can see it's a 32-bit executable. You can check the ASA. The hash is the same as on the VirusTotal. There's not much interesting in here. You can see there's not so much imports in this file. So interesting imports for us would be definitely create file, find first file, find next file, and we can see there's a load library and get proc address. So probably some additional imports might be resolved inside the code. But yeah, there's not that much interesting in the strings, although we can see there is some string that is related to the physical drive 0, which is basically our physical drive, meaning our hard drive physical representation. And so that's already definitely interesting. And something more we can see is like this string, your hard drive has been corrupted, and in case you want to recover all hard drives, you should pay a ransom. But let's take a look at our file in Ghidra. So I already have it in Ghidra here, and there's a few ways to look at it in Ghidra. We can go to the entry point, go through all these functions, see what they do, or we can remember that we saw that create file W call that looks interesting, or even the write file call that also looks interesting for us. And if we see when it's referenced, you will see it's actually referenced in this function here. So, and this function is pretty interesting because if we look at this function here, you can already see it calls the create file W, and then after it calls the write file function. So it creates some or opens some file because create file can also open files, and then writes to it. And what file it opens is even more interesting because it's a little bit unclear here because of this stack variables, but we could clear it up. But if we look at the Microsoft documentation, we can see that create file W takes first the file name, then the desired access, then some other things, and it basically returns a handler to the file. So based on these names, even we can see that this one is the file name that it opens, and this is the access actually. So if we look at the access as well, we can use the setEquate function. And look for the one related to the access. It's actually a perm or access mask. So we can see it opens our physical drive 0 path, which is basically beginning of the physical representation of the hard drive. So it opens a handler to the physical hard drive, and then it writes something to it. And if we look at the write file function documentation, we can see it first takes the handler to the file, then it takes a buffer, number of bytes to write, and buffer to number of the files written, and the last one is not in use. So if we see here, we can already see that the handler, the first handler, is our handle that was returned from the create file W. And the second one, the second option, the buffer that will be written here, it should be in this local variable 2020. So, and the fourth option is the size of the buffer. So the size of the buffer is 0x200, so 200 in hex, meaning, if I'm correct, it means, yeah, 512 in decimal. Anyway, so it will overwrite first 512 bytes on our disk with some buffer from here. And if you know or you Google the first 512 buffers on the disk, it is the exact size of the MBR buffer, so the master boot record buffer on the disk. It's always the first 512 bytes. So what is it overwriting it with? We can see where is this buffer taken from, and we can see it is being initialized here, but then it's being assigned to this local variable 7. But actually here we can see the variable 7 is copied to the variable 6 for some reasons. Anyway, if we look at the variable 6, we can see the buffer in here. And if we double click on it, it will take us to this buffer. And it doesn't look interesting at first, but at some point we can see this string we already seen. So your hard drive has been corrupted, blah, blah, blah. And what we can do is actually we can take these 512 bytes, meaning 0x200 in hex, from here until, so it's from 404020 to 404220, if I count correctly. 404220 is here, so actually until here. And we can copy. We will copy special, and we will only copy bytes without spaces. And then if we use our hex editor and open a new file, we can actually paste it here, and we have our entire MBR buffer that is being overwritten by malware here. And if you notice something, maybe you don't know, but if you Google it, MBR buffer always have this signature at the end. Unlike most files that have the signature at the beginning, it's related to the fact that some backward compatibility, etc., it has to start with the code. But actually it ends up with the signature, and the 55AA signature is the signature of the MBR sector. So we can save it, and we will save it as a MBR, for example. And we can even check with our file utility, and it will tell us that the MBR file we just saved is a dos/MBR boot sector, which is great. So we know that it will overwrite our MBR buffer with this. But what this code actually does, we can suppose it's displaying somehow this ransom note. But we can actually analyze it in Ghidra as well. So let's load our newly saved file to Ghidra. And because it's a master boot record, it operates in the real mode. It's a special mode that the old machines, old CPUs work in. You can read about it. And generally, master boot record is written in the 16-bit assembly real mode. And if you load it like this, it will then load it correctly into Ghidra, otherwise it will generate an error. And you can analyze it, of course. There is actually one more thing to do. So if you Google or find in the documentation, actually I found it in this kind of CTF write-up, which I will also link in the description below. Someone was analyzing the master boot record, and he said MBR entry point is at address 0x7cc0, so the memory block has to be moved manually. So actually that's what we have to do by clicking the memory block here and moving it to 007c00. And then if we do it, and if we click on disassemble, we should have our function in here, our code. And the code is quite simple. So basically there is a for loop that for each character from this string we already saw about the hard drive being corrupt, it executes some function. And if we look at this function, it's not too long, and it might not say us anything if we look at the decompiled code. But actually, if we look at the assembly, we can see it's moving this number 0xe, meaning 14 in decimal, to our A8 register, and then executing the interrupt number 0x10, meaning 16 in decimal. And this is interesting because your interrupts, as you may know, are the the lowest level way to communicate with a processor and tell a processor what to do. And create interrupts generally. So if we look at this interrupt at Google, we can see that the interrupt 10H is the shorthand for BIOS interrupt code, blah blah blah. And generally, it's a remote interrupt handler. It's a interrupt that is being handled by a BIOS interrupt handler. That's not really that much important. I will also link it under the video. You can read more about it. But basically, what it does, it creates an interrupt for a processor, and it tells him what it wants to do. And for that, it sends this function code. So the function code is what we have seen in our register AH. So our function code was actually 0e. So if the HH is 0e in hex, it means teletype output, meaning it will just output text on the screen, as far as I understand. So in general, we can see that for each character from this string that just disappeared for some reason from the decompilation, but we can see it here on the assembly. It will execute this interrupt by telling the processor to just display the character on the screen. So it's like a very low level and old way to display characters on the screen. Of course, now in the higher level languages, we will use functions like a printf, etc. But in the end, this will be translated somewhere in the kernel to the interrupt. It's not necessarily this interrupt, but some interrupt. But yeah, in this case, we are operating directly in the master boot record sector, so we don't have such high-level functions. So the attacker who write this this malware had to use this kind of low-level techniques to display the string he wanted. There is a little bit more to this code. It's not actually a very long code. The entire MBR sector only has 512 bytes. But if you look here, actually below this function, there is some additional do while loop. That's really looking at this decompiled code, not so clear. But if we look at the assembly code, then it will become a little bit more clear. So we can see clearly here there's another interrupt being sent to the processor, to the external devices. And so this interrupt has number 13. So what does it mean? We can check on Wikipedia or another sources again. So we see before this interrupt, some of these registers are being set up. So let's see what our interrupt number 13 is. So if we look at either Wikipedia or the OSDev wiki, which is also interesting, the interrupt number 13 is a disk access interrupt. So it's a BIOS interrupt that's being used for accessing the disk for both read and write purposes. So you can also see this in the Wikipedia. So there are like different modes depending on what the AH register is set into. In our case, it's actually 43. So if we look at this, 43 is extended write sectors to drive, and AL in this case is being set to 0. So meaning there's no write check after the write. The drive index in this case is set to 80 in hex, meaning first hard write. You can see it here clearly. And then we have something written to the SI register, which is basically pointer to this structure here. And this structure here is something called the DAP structure. This is actually better explained in the OSDev wiki. So you can see here, this is the structure of the disk address bucket structure. And first is the size of the packets, then the second byte is always 0. Then there's a number of sectors to transfer, the pointer to the transfer buffer. Not really a pointer, it's more like LBA address, so address of sectors times 512. You can Google it, it's also on the Wikipedia how the logical block addressing works. And then there's a lower 32 bits and the upper 16 bits of the starting LBA. So basically it gains the pointer, in the end it gains the pointer to the buffer and the pointer to the sector on the disk it should write into. And then it basically writes from this buffer into this sector of the disk. If we look at our code, it actually writes from somewhere here. So it writes itself again into the second sector of the disk. So actually the disk number is the sector number is here or here. I don't really remember. So anyway, what it writes is we can check on Wikipedia again, actually, that's what you normally should do. So the transfer buffer is just a transfer buffer, but the number of sector to transfer is here, and the lower 32 bits and the upper 32 bits, so last 8 bits are actually the number of the sector, but it's just one in our case. So it's the I'm assuming my OSDEF knowledge is also not that good. It's just a second sector because probably starting from 0 that it will write into, and what it writes into is just basically this data, which is at the end of the structure. And we can see this in action in a while. Why it does it? I'm not really sure. Probably most likely to kind of even more destroy the initial sectors of the disk and maybe make a recovery of the MBR harder. That would be my guess. I'm actually not sure why it does it, but yeah, I'm just doing the full analysis of the code, so I wanted to show you also this. And we can also see it in the live dynamic kind of analysis, which I will show you just now. Well, let's see if our analysis was correct, if what we saw in the static analysis was correct, and how this malware really behaves in the normal environment. Of course, we won't destroy our MBR on the normal physical machine, so we need to use a virtual machine. I chose to use a different Windows 7 machine on the VirtualBox for different reasons. The main reason being Hyper-V does some additional checks in UEFI for the MBR sector and the booting process. Kind of like secure boot, but even if you turn off this secure boot, it still works. So it's just gonna say this MBR is corrupted, and I'm not gonna launch the system, but it's not gonna display this kind of cool ransomware node. But VirtualBox will do it. So, but it's gonna work on Windows 10 as well. I'm just using a Win 7 machine that I have on my VirtualBox. Anyway, also on the left, I have opened it's the VHD drive of the virtual machine, but any drive is fine. It's a flat VHD image, so you can see everything that's happening live. And these are the very first sectors of the VHD drive of this machine's physical, let's say, drive, because for this machine it will be visible as a physical drive, even though it's a virtual file on my host. And you can see the first 200 in hex bytes, meaning 512 in decimal. It's some kind of a code. which is the true MBR sector for this machine. Right now, it has some strings like invalid partition table, error loading operating system, etc. I'm not gonna go in depth what it's doing right now, but we will have it here on the left, so we can observe how it changes. For the physical machines, you can also use like an FTK imager for the same purpose. So you can actually add evidence item, mount the physical drive, and then you can see exactly the same. So it's the first sector of our drive. You can see it's the exactly same as here. We'll be using this hex editor on this virtual drive because it's simply easier, but it doesn't really matter. So I will launch this stage one malware right now. Just notice I'm using the administrator elevated command line. So modifying MBR and accessing the physical drive directly, it requires elevated privileges. So the threat actor needs to elevate privilege somehow before running this code. That's also something to note. So just observe the left side of the screen and what happens when I run the code. So I'm running this code now, and it has some error, but it doesn't really matter for us. What it should do, it should change the MBR. We can also check in our FTK imager because the file can have some delay. So we can do the same, like mount the physical drive. And then you can clearly see it's being modified. And now we have this your hard drive has been corrupted, blah, 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 pay us money node in our MBR. So I just reloaded it. And you have to, so now it's already modified. You have to believe me, it's modified live when we executed this malware. But we've seen that also in the FTK image. Now, let's say we are the user and executed this file, someone executed it for us, and we simply reboot the machine. So, and see what happens. So after we rebooted our machine, you can see this. After we rebooted our machine, you can see this ransom note. Oh, your hard drive has been corrupted. In case you want to recover all the values, you need to pay 10K. But of course, it's not gonna do much because even if we pay it, the organization who done it, they don't have a capability to recover our MDR. It wasn't encrypted. It was just simply wiped and replaced with something else. So that's not gonna help all that much. And you can also see there just used to be these first 200 bytes, and now it added some additional 200 bytes as well to another second sector of the disk. Last thing to talk about is, can we actually recover from this kind of message? And the answer is, yeah, it depends. Well, if the only stage one was executed on our computer, then we can definitely recover files. And it's quite easy because the files haven't been encrypted and they are still somewhere there on the disk. So if we just look through the drive, they will be there. You can use the tools like test disk or photorec or something to recover data. But preferably always, if the data is important, always use the data recovery specialist. They will do it without destroying your data by accident in the meantime. Um, can you recover the MBR and fully recover the system? And the answer is you should be, but it really depends. So actually, I tried to do it in the VirtualBox using the test disk utility and using like Windows recovery disk, etc. And even though I recovered the MBR to the previous state, the machine was not booting for some reason, and I didn't have time to debug it. But I did the same on Hyper-V, and it actually worked. So on your physical machine, someone better than me in the recovery of these kind of MBR files and the boot system should be able to recover it. So uh, the malware itself is, of course, destroying this first sector of the disk, but all the partitions and all the data is still here. So theoretically, it's possible to just recover to this disk to the state it was in based on the data that's in there and just put your system normally. But of course, this malware also has a stage 2, which destroys your files, and that's the part that we'll talk about on the next video. And this is it for today's video. Perform a static analysis of first stage of WhisperGate, malware that erases your MBR sector and replaces it with a ransom note. We also saw it in action and understood how it works. In the next video, we will analyze second stage of the same malware. What it does? Well, see the next video and find out. I hope you liked this video and see you next time.